G'day everyone, how are you going? This is a review of Test 2 Functions and Graph Sketching from our Specialist course. It's syllabus dot points 3.2.1 to 3.2.8. Only a few number of dot points, but there is a lot in this stuff, And also it's stuff that often comes up in the WACE exam and really tests people towards the top end. This stuff can get really complex, so my advice is review this test, look over it a number of times, resit the test. I made this test quite hard, I'll be honest. This is not an easy test. There were lots of spots where a strong knowledge was needed to get even kind of 50% of the marks in a particular question. So if you scored in this test a pass, you've actually done quite well. If you got over about 65–70%, you've done quite well. So use that measure for this particular test. Because we're coming up to exams fairly shortly, I did want to make this test a little bit harder. We are not doing test 3 this year, so this is our last opportunity to actually get this in play. So here we go. Let's have a wander on through. If my assistant can roll us up, there we go. I'll jump over this side. So this one, we've got two functions. This is our composite function idea. Now, work within the first one in here, right? So -1 I've put into g of x and I've got an answer out just by using this one here. Then I've taken the 4 and I've put it into f of x because I know g to the -1 equals 4. So 4 is slotting on in there, which slots it in there, which makes this one right here. Should have been fairly easy with that, only 1 mark for that. Next question. Now in fact, doing this question first may well have been easier for you because this is working out f of g of x, which is what the first question needed you to use. Now what you should do here is work this one through as you can see. Now if I then put x equals -1 into here, I should get exactly the same answer that I did here, and indeed I do. So that's a bit of a double check. I was working out the composite function. Well, if I put -1 in here, the answer I get should be the same as that, and it would have been. So that was a double check if you needed to. Moving on. Now we're looking at the domain and range. This is really good notation. My recommendation is to use notation like this. What does it mean? Curly brackets. I am defining a set of x values, hence it is the domain that I'm defining, such that I'm drawing from the set of real numbers. So I'm excluding all the imaginary numbers and all the other kind of rubbishy numbers. I'm only looking in the real numbers. And then I'm saying, well, I'll take all of those except x equals 2. Now I can't use x equals 2. Look at it just here on the screen. If x equals 2, then the bottom line equals 0 and the function's undefined. So this is my exclusion right here. Okay? The range, I've got to then think what values from that, move it down a little bit, what values from this can I not get out? And the value I'm not going to get out is 0. You should recognise this graph, forget the 2, is a 1 on x graph. So I'm going to have a little bit here coming close to the axis and a little bit here coming close to the axis. So that confirms that the y cannot equal 0, or the range cannot equal 0, or f of g of x cannot equal 0. Now one note from someone that did this question for me. I've used y here and I wouldn't have a problem with that. But let's be clear that we're not really graphing y, are we? We're really graphing the f of g of x. Okay, and the question always referred to the f of g of x. So I probably should have had f of g of x in all of these spots here. I don't think you'll lose a mark for it, but let's be clear that we're not actually graphing y, we're graphing f of g of x. So we probably should be true here. Okay? Move on, next question, here we go. What do we got now? Oh, this one, right. So we're given this graph here, and this is quite important, that we're only between 0 and 8. So we're only picking up this part here. And the second important thing is, because it's the square root of, we're only taking the positive part of that. If this had been given as f of x squared equals this bit inside the bracket, then I'd have to take both parts, the positive and the negative. But here I'm only being given the positive, and I'm only between this range, or this domain here. Alright? So a bit of important information up there. Right, what are we doing? Leave that right there, that's perfect. In order for the inverse to exist or to be a function, right? Function meaning vertical line test. It's got to pass the vertical line test on the inverse. So that would mean on the original, I've got to make this pass the horizontal line test because all of these values become these values when I do the inverse. So this is not going to pass the horizontal line test. And if I look here, if I take from 3 the highest point and knock out that part of it, then this part here will pass the horizontal line test, meaning that the inverse will pass the vertical line test. Okay? And what have I got here? Well, f to the minus 1 is not 1 to 1. That's why it will not be a function as it stands. But if I restrict it to only values greater than 3, that being the minimum restriction, if it just said make a restriction, you could have said less than 3 as well. Okay, 3 or less. But because I want to do the minimum restriction, knocking out 3 in the domain is a lot better, or it's a smaller value, than knocking out, 5 out of the domain. So if it didn't say minimum, there'd be 2 answers here. But because it says minimum, I really have to knock out the 0 to 3 part, leaving the 3 to 8 part, and therefore then the inverse is then going to be a function. Cool, a lot in that one. Let's move on. Next question. Right, now, with that restriction from A, greater than or equal to 3, we then need to determine the inverse and its domain. This is pretty tricky stuff here. What you needed to recognise was here we've got some form of a quadratic. It's not going to factorise neatly yet, but we've got a bit of a quadratic under there. If I square both sides, I can get rid of the square root sign. That makes it neat. Then I've got to recognise y squared and 6y. If I bring that together, here it is. Notice I've changed the signs, but I've also made this negative. Then if I add 9 and take 9, well, here's my perfect square now. I've got a perfect square, and here's 25 left over here. Okay, I'll come through to this. Move a few things around, you can follow it through, move a few things around, and I come down to this one here. So that is my f to the minus 1 of x. Okay, swapped everything around, I've come around to that one. Now what I've got to recognise over here, let me jump the other way. The domain of the inverse is the range of the original. The domain of the inverse is the range of the original, because you remember they swap over. Okay, so therefore, if I look for the domain of the inverse, I can just go back to the original function, remembering using the restriction. So I'm including that restriction. So if we can scroll back up to the top, here we go, a bit further. There we go, yep, here we go. So I've already made that restriction there, haven't I? I've cut this part out. So if I take the range of the original, that would become the domain of the inverse, and right there, 0 to 5. So 0 to 5 was the range of the original with the restriction. So that therefore means that it's going to be the domain of the inverse. Oh, blue screen, what's going on? There we go. And you see the same notation here, picking up the same notation. Let's keep moving. Lots to see here, lots to see. Ah, this graph, this is a cracker. Have a look at this one, a little bit higher, a little bit higher, there we go. Have a look at this one where it all falls in, and then I've got a whole lot of working down below. Key things, from the graph above, you'll have it in front of you. From the graph above, we get this one and this one as asymptotes. When we divide the top line by the bottom line, we get the oblique asymptote. Okay, so we've got 3 asymptotes we've got to pick up. If we take the derivative of the function and let it equal 0, we get these 2 turning points. Okay. If we look either side of this asymptote, on one side we get a big positive number. On the other side we get a big negative number. So that confirms that it's a regular asymptote. Okay, what you would expect. But when we do the same around this asymptote, you notice that the values of the graph are approaching the same point. Now, because they're approaching the same point, but cannot exist on that line, we call it a point of discontinuity. So the graph just stops minuscule before and starts immediately after. So it's not an asymptote like this, where it gets closer and closer and closer but never touches. It almost rams on in, stops just before, and then starts just after. Now, the key with this, even if they put this in a calculator section, you put this on your calculator, you won't see that. You've got to zoom in and zoom in and zoom in and zoom in about 50 million times before you will see that on your calculator, because the resolution on the calculator screen is not enough to see it. So just because this question's in the calculator, it's not here, but if it was, don't go, oh, that's easy, there we go, done, oh, I can just copy it off the calculator. I almost guarantee you guys are spec people. I guarantee you in your waste exam at the end, somewhere, this guy will be hiding, right? Because it really tests, did you know what was going on? How do we spot it? Well, this asymptote and this asymptote are easy because we get them from solving the bottom line equaling 0. Okay? So that tells you that something has to be happening up and down this line. You would have looked at this asymptote either side and picked up that it has to be here. You know it has to go through that turning point, and then you're going to say, well, where's it got to go after that? Well, the line of y equals x, you know it's got to end up here, right? The only thing I can think you might misinterpret would be you might make this do this and then curve around here and come down there, right? I can see how you might think, oh, I've got to come close to that asymptote. But where you know that is not correct is that you only came up with 2 turning points, right? If this graph was to turn here and go down, then you must have a 3rd turning point. But you didn't. You only had 2 turning points. So therefore you can't add another one in here. This one's okay, and this could have gone like that, but you can't add another turning point in. So that's the key to say, well, I can't put another turning point in. I've got to end up over here, and I've got to start over there, and I've got to go through that. So the only thing I can do is cross over that asymptote. Hence, I must have a point of discontinuity there. All right? Very important question. Scroll on up. Let's have a look at all the working. All right, this is all the working. Now, I'll leave that up just for a moment while you might want to pause on the video. I'll jump out the way. That's all the working that you need. You've got to look as x gets to large values, take the derivative, let it equal 0, solve it, get these values, get your turning points, let the bottom line equal 0, get your asymptotes, work this one for where it crosses over the y-axis. Have a look here and see there's a bit of an issue here. That's the point of discontinuity. Look either side of your asymptote to find out what's going on. There's a huge amount there. And because, scroll back up to the top for me, right to the question, because it said clearly showing key features, you needed to, on your graph, label all these things, right? So don't just label them with no working. Show what you're doing. It's a lot of number crunching. It's a lot of work. But hey, it's 6 marks. You got 5 or 6 minutes to do it, right? So very good question to review and review and review. Let's keep going. We're into the calc section now. Here we are. Right, now the first question should have been really simple. Should have been really simple. You've got the equation, you've got your calculator now. It was really just, can you put it on the calculator and can you copy it neatly? Now, my question said, ensuring all key points are labelled. That's me saying I want to make sure that you can put it on your calculator, you can use GSolve, you can find all the points, you can copy them and put them on there. Notice, turning points, intercepts are labelled, turning point is labelled, y-intercept is labelled, asymptotes are labelled, right? 2 up there and 1 down here somewhere. Where'd it go? There we go, at -4. Okay, so I've got all the points labelled on there, and the last point that I gave was for a smooth shape, so you've connected all that together well. This shouldn't have been a difficult question, 5 marks. I know drawing can take a little while in a test. 3 or 4 minutes is really what it should have taken you on this one. This one should have been fairly easy for you. Next question. Right, classic question. This has been in almost every spec exam in the last couple of years. Here we go, here's a graph. I don't care what the graph is. Now I'm going to test, can you manipulate that? Inverse, reciprocal, absolute value. So keep that in your mind. Cubic, positive cubic. This one reflects in x equals 0. Oh geez, I made a mistake. This should be a y. Reflects in y equals 0, isn't it?
That is y.
That is y. There we go. Look, kind of looks a bit like an x. Okay, I'm going to say it's a y and say that. It reflects in y equals 0. So this graph originally would have done this and had another turning point here. We throw away the negative stuff and just flip this on over. Okay? 2 marks. If you knew what you're doing, it was an easy 2 marks. Next one. I think it's, okay, so the inverse. This is where we're drawing the line through here, y equals x, and we're flipping it over that. Now, can I make a note here that what the markers will look for is, have you hit this point right here, the turning point, this point right here, the turning point. That's the points they're going to look for to make sure you knew what you're on about. Okay? So, take your x and y values from your original, swap them over, right, and bring them over here. Okay? Because by swapping them over, you will move it from wherever it is, somewhere here, I think, over to here, and from somewhere here over to here. Okay? Then if you get the x-intercepts from the original, make them into y-intercepts, you'll have a whole lot of points. It's connect the dots. Okay? Please, please, please make sure that you get these points in the right spot. That's what they're going to be looking for. 2 marks, easy marks it should have been. Next one. Now, bit more work in this. This is why it's 4 marks, because remember, this is 1 over f of x. So therefore, hold that exactly where it is. Therefore, on this, wherever it crosses the x-axis, that is a y value of 0. So then 1 over 0 is undefined, hence why these all become asymptotes, right? And then just work within each one. Now remember, here are the key points you want to hit with this. Because this is 1 over f of x, on the original graph here, any points that run through the line y equals minus 1 or y equals positive 1, they stay in the same spot. I'll say that again. Any values that lie on the line y equals 1 or y equals negative 1, they stay in the same spot, because 1 over minus 1 is still minus 1. And 1 over 1 is still 1. So notice how I've dotted in all of these points here, right? You can see a little dot where I've put a dot going, I know I have to go through that, all right? Then I've just kind of connected the dots together, basically. These ones here are the other 2 key points. Can you scroll up to the original for me? So on the original, now note this. This turning point here happens, it looks like a little before 1, a minus 1. Don't get too worried about that. But it happens at about 4, a smidge more than 4. Hold that in your head. This one happens a smidge after 8. Okay? So it's a smidge after 4 and a smidge after 8. Back to our answer. That means that this point right here has to be 1 over 4. So that's got to sit at about a quarter, and this one has to be 1 over 8 right there. Now, if you don't get them exactly, that's okay. But a few people had their turning points up here or down here, so clearly you hadn't picked that up. So wherever the turning point is, calculate 1 over that. Get a rough approximation so that you can dot these 2 in and actually have them correct. You could, if you wanted to, actually, because it's 1 over 4 and 1 over 8, or approximately so, you could actually put a little arrow there and say approximately at y equals 1 over 8. Approximately at y equals 1 over 4 to tell the marker, hey, I know where all this goes. These questions are easy to get lost on. Easy to get lost on, but they shouldn't be. They're not that hard a question, I don't think. Okay? If you've practiced a number of them and you know about these points, you know how to get your asymptotes, I think it should have been a relatively easy 4 marks. Question number 6. Right, now we are heading into the cracker of a question. This is about the hardest question I think you could ever possibly get in this course, in this section. Now, importantly, we've been given y squared. Right, you remember earlier in the paper I said you've been given y, I think it was f of x equals the square root of, so we only take the positive section. That was, where is it? I've got it here, Oh, where is it gone? There we go. That's that question there. Right, that one there, we only had the positive part of the graph. This one is giving us y squared, so we have both the positive and the negative part of the square root or of the function. So we can write it like this, but we've got to recognise we have both parts. Because we have both parts, I'm probably going to end up with more solutions than what I normally would or what I'd normally expect. By Calc, I've taken the derivative of it. It looks kind of funky, but I don't really care. I've got a calculator for that. Solved it equals 0 as I came out with plus or minus 2. Now, I'll show you something in a minute about the calculator. This then comes up with this. When I take plus or minus 2 and put it in there, I end up with multiple answers. So there's actually 4 stationary points. That's going to be really handy when I come in down here. Now, my point about this is when you graph this on your calculator can't graph y squared. Okay? You actually can in the conics section, but in the graphs and table you can't do y squared. You've got to put this in. But when you put that in, the calculator will only see the positive part. Right? So you've got to go, hang on, I'm telling the calculator to graph that, the positive part, but I know whatever it shows me on the top, I know it must flip over and be on the other side because it's plus and minus. So you've got to think, hang on, the calculator's not telling me the full story because I only gave it part of the equation. I've got to see that there's more and flip it over the x-axis. So that's an important kind of thinking there around what we're going to get. Determine the equations of the asymptote. Right, so if we let the bottom line equal 0, then that is going to give me points on the graph that I can't get to, just like we've done in many others. Pretty easy here, plus or minus 1. 1 mark there, no problems at all. But maybe there's more, and I get it, you might not have seen this. By division, synthetic, algebraic, however you want to do it, right? This is what it comes up like. Notice it's y squared. So therefore, when I take the square root of it, I get plus and minus. Okay, plus and minus. So I end up with this being my equation of another asymptote. Okay, it's a curved asymptote, but another one. Now, then I've got to think, well, what's actually happening with that? And that's where this is important. Think about this. As I go to large values of x, I'm on the extremes of the graph, large values of x, I'll get a really large number here, just leave it as x squared for the moment, plus a tiny number. This part here, as x squared gets larger and larger, that thing gets smaller and smaller, doesn't it? To the point where it's, if x is 1,000, then this part here is tiny. So I just literally forget about it. It's so tiny, don't worry about it. And if x is, say, 1,000, then this is really, really big. This, relatively, is really, really small. Forget about it. So you can basically forget about all of that part there. All of that there. Right? Get rid of that. You've then got x squared square root of, well, that's just x, isn't it? Plus or minus. So this part all disappears when we're looking at large values of x to see what is this thing doing at the extremes. We know around here the graph is going to come close to here, right? We know that. But what's going to happen at the extremes? We'll look at this one, right? And that will tell us this information here. That at the extremes, y is going to be equal to x and y is going to be equal to negative x. So we're going to end up with a cross going over our page like this. Scroll on up to the graph, and this is what it looked like.
That's right.
It is, isn't it? It is ridiculous. I agree. Crazy ridiculous. Good ridiculous. So we've got our two asymptotes, positive 1 and negative 1. We've then got y equals x and y equals negative x. Now, if I wanted to go a little bit further, and I didn't put it on here, but jump on your calculator, work out the turning point. Oh, actually, no, I lied. We've got them up top. Yeah, we've got the stationary points up top. So dot them in. And then similarly, you kind of go, well, I can't really do much more than start down here and then head on up there. Now, if you graph it on your calculator, you only get these two. But of course, remember, you've got to think, hang on, I only told the calculator half the story. I know they've got to exist down here as well. Okay? Now, I will apologise in one small way because the question here, I used a question from a past waste exam but changed the equation at the top. I probably should have given you a centralised graph here. See how I've given you 0 to 8 here, but only 0 to 4 here? I probably should have centralised that, but the tuning points and everything still fit on, so it's still able to be done. But I can understand how you might have gone, oh, why does it look like that when the graph doesn't kind of sit in the middle? And if you're a smart exam taker, you would look and go, maybe I've done something wrong because they gave me the graph like this. Maybe something's not right. So I understand if that came across, That wasn't the intention. It should have really, the axis really should have been here, making it +6 and -6 both ways. Having said that, it all still fits fine, so I don't think there's a huge issue. Let's move on. I think we've got 2 questions to go. Maybe 1 to go. No, 1 to go, 1 to go. Alrighty. So we've got 2 graphs. We don't actually know the equations of them, but we've got 2 graphs. F of x and, H of x and G of x. They're obviously absolute value graphs because they've got a bounce in them, okay? This one, G of x, that looks to me like it's the original. It's taken the, it's moved across, so I think it would be x plus 2 to get it across to here, and then the absolute value of it. We didn't need to work that out, but it's not a bad idea to think it through. This one, I think that, because see how it goes through 0, 0 there, I think that's just y equals x to start, right? It then was the absolute value of y of x. That would give this, right? And then, oh no, I've made a mistake. Sorry, start again. I think because we've got this here, I reckon what we need to do is, if we had y equals x, yes, we would go through here, but I've got to pick this up. So I actually think we've got to have the graph here originally, which would be x minus 1, right? That would be like this. Take the absolute value of it, that would bounce it this way. Make that all negative. That would flip it over and be now here, and then add 1 to it. So there's a couple of things going on with that one. We've got to move it, we've got to absolute value it, flip it, and then move it up again. Anyway, we didn't need to do that. We needed to work out k if this is the case. Well, look at this. What I would do is this, is that if we work out g of 2, which we can go and read it off the graph, we know what that is. So we know what g of 2 is, it's equal to 3. So then we just need to work out h of 3, and we end up with -1. So just step through the graph, okay? Using the graph up above to find these particular values. Good work, here we go. So g of 2. So this one is g of x. Oops, stop. This one is g of x. So I've gone to x equals 2. I've gone up and I've gone, okay, so g of 2 is equal to 3. Then what I've done is said, okay, now that I know g of 2 is equal to 3, take that value of 3, the range or the output value of g of x, and put that into h of x. So then I would go from here, the output value of 3, to here, to put an input value into h of x, and that would get me my -1. So I'm starting on the x value, going to the first function, picking up an output value, and then using that output value as the input value of the next one to find the -1. Lots going on. All right, next question. Now this one. This is a good question because we get multiple solutions here. Right, let's have a look. Again, I've kind of done the opposite here. I've said forget about this h of k business in here. Just read it as g of x equals 1. Now from the graph, don't move this time. From the graph, g of x equaling 1, I get 2 solutions out of it. Right? And then I've said, well, okay, if g of x equaling 1 gets these, then what I've got to do is make h of k equal to that one, or h of k equal to that one. And of course then I'd go to my h of k graph, and again, because it's a absolute value graph, I'm going to end up with 2 solutions here and 2 solutions here. Okay? So I actually end up with 4 solutions. And because the question only said determine the values of k, didn't ask for coordinates or anything like that, so writing it like this is fine. You can see 1 mark for the first 2 solutions, or any 2 really, and all solutions got you a 2nd mark. Over the page, I think we're on to our last question now. Last question, here we go. This one's a great one, I like this. So we've got this. If we know our absolute value stuff, this wouldn't be too hard to get the values of, I don't think. Similar to the one I did in the earlier page, we can just see where we're going. Start with a graph here, get the angle right, move it where you need to, take the absolute value of it, shuffle it on down. Okay? So we had the values here, a half, -3/2 and -2. 1 mark for each of those. Okay? Now, the next question, leave it where it is for the moment, the next question is taking the absolute value of the function that we know. The absolute value of what we were given, and then we want to find a line that will give an infinite number of solutions. So to get an infinite number of solutions, the line that we create will need to lay right over the top of the graph that we create from here. So scroll up here for me. Right. If I take the absolute value of this, remember f of x is already an absolute value, but if I take the absolute value of f of x, that will take this part that's below the x-axis and it will bounce it up here. So the actual graph will be if you like, a double bounce. Okay? Scroll on down again. I've got a little diagram of this. There we go. So this is what it's going to look like. It's got a double bounce in it. Okay? That's the absolute value of f of x. So there was a mark if you recognise, hey, what is this going to look like? Now then I think I'm going to get 4 solutions, because if I want to match a line to this, I could have the line right here and therefore get infinite solutions. I could have the line here, get infinite solutions. Or here, or here. There's 4 different lines that I could draw which would lay over the top of that. Once you've recognised that, it's not so bad with the numbers that you've got here to see what would be going on. Right? I don't think getting the lines is too bad a job once you see what's going on. And I think the question said, determine the values of the positive constants m and c from that linear equation. So these lines, look, I would have paid it. I would have paid it here. But in reality, I probably should answer like this, because it was only asking about the lines m and c, the values m and c. It didn't ask for the equation of the line. It asked for the values of m and c. So that's why I did this. I said, well, I'm going to give you the values here, m and then c. Here you go, here they all are. Okay? Now, if you notice, this one and this one, once you've got one of them, you just make where they're negative, make them positive, where they're positive, make them negative. Look, that one became positive, that one became negative. Over here, the same. Positive, positive, negative, negative. So you kind of only needed to get 2 lines and then recognise that just that part there could be an individual absolute value. So that line, make the m and the c the opposite sign, you'll get that line. Once you've got that line, you'll get the other line. So you could kind of see it as 2 separate absolute value graphs, and that would speed you up a little bit in getting these. All right? Now, I tell you what, that's the end of part B. This is a tough paper. There is a lot of little spots here you can get trapped, not know what you're doing, not see something. There's a lot of tricks in this. My advice would be, park this paper for a while, maybe a week or 2, so you're about a week away from the exams then. Sit down, do it. Right? I'll put these up on Sector. If you're not in my class, you want a copy of this, email me. I'll put it in the description below, and I will send you a copy of this paper. More than happy to. It's a great paper to do. It really is. It'll test everything you need to know in this section of the course. Hopefully that's been helpful. I know I've raced through. I kind of have to. There's so much in this. Enjoy. Good luck for your exams. See you later.